why do we actually need VORs? How did they come into being? Well, NDBs suffer from a series of problems, which we've already talked about. Things like they function slightly different during the day and the night. They suffer from coastal refraction, and where the radio waves can bend along cliff edges and things, only by a couple of degrees. They suffer from reflections, where as an NDB goes behind a hill or something like that, you can pick up the NDB being reflected off another hill, which causes the needle just to briefly deflect to somewhere else. So they've got a couple of small issues that you've got to think about when you're using them. But the biggest problem with NDBs is twofold. One is they're not actually that easy to use, because when you're using them as what's called a command instrument, in other words, when you're physically flying to and from them, as we've already discussed, is if you're flying from an NDB, it doesn't matter where you are relative to the NDB, but you'll always get a display with the needle pointing straight down as you fly over it. Doesn't matter what heading you're on, provided you've gone over the NDB, it will always show it as straight behind you, because obviously that as you go over an NDB, it doesn't matter what heading you're going to be on, it's always going to be behind you. That means tracking away from an NDB requires a fair bit of skill, and it's very difficult to compensate for the wind when you're tracking away from an NDB. You've really got to have gone to the NDB first to found out what the wind correction is, so that you've already made that correction when you're flying away from the NDB. But the biggest problems that NDB suffer from isn't all these technical issues and the fact they're a little bit more complicated. It's more of a historical thing, in that what happened is that as navigational aids started to increase, people realised that maybe what was required with aviation is to divide up a series of airways around the world, and what would happen is you would have beacons at these intersections, and planes would be routed all around these airways, and you'd be able to fly to here, come down here, and planes would then be vectored into all these different airways here. If I can remember what amber one looks like. But you would have your Atlantic traffic coming here and here, they'd be merging here, they'd be coming down here, and so you'd have all of these NDBs all around the place. So you would need an awful lot of NDBs. Now, NDBs have one big thing going for them, but the one big thing they have going for them is also the one big thing that works against them if you're trying to try and do lots and lots of them, in that NDBs work in the medium wave band. Yeah, all right, sometimes right off the end in the long wave, and sometimes a little bit there, extending a little bit further than the medium wave band, more into the sort of lower short wave bands and things. but they're basically medium wave. Now, medium wave signals tend to follow the Earth, so they can bend around the Earth's surface. They can also, depending on what frequency they are, they can bounce off the upper ionosphere and all sorts of things, which means their range can be huge. And there are some NDBs, for example, in the Pacific, on some of the islands, the NDBs are transmitting at like a couple of thousand watts, and their range is 2,000 miles. And we've had even instances in the UK where on very, very weird evenings of atmospheric conditions, we picked up NDBs of the from South America and all sorts of things. I mean, NDBs can have huge range, but that's also their big downfall, because if you want to cover the world in NDBs, and you want to have all of these airways with NDBs at every intersection and things, if they can have a range of 1,000 miles, well, that means that each NDB has to be guarded from another NDB's frequency to make them all unique, within a range of like maybe 500 or 1,000 miles, even if they're relatively low power, which means you need to use an awful lot of the frequency space just dedicated to NDBs. Now, the medium wave band is also commercial radio. It was certainly back in those days. And commercial radio operators, they needed the medium wave band, and it wasn't possible to steal the entire medium wave band just purely for aviation. And of course, these medium wave operators were also jumping in on the act and stealing aviation frequencies and things and creating interference. So what was required is a fundamental rethink of the way beacons work. And maybe in this fundamental rethink that came along all these years ago, that they could probably solve some of these unique technical features of the NDB and these complications about flying away from it and all these other things, and maybe add a few more features at the same time. And this was basically the birth of the VOR. So, how did the VOR come into existence? Well, first off, they chose a frequency where the range is fixed. By the range is fixed, I mean they chose a frequency where the radio signals don't travel around the Earth's surface. They don't bounce off the ionosphere. They're not ducted. In other words, that they're line of sight. And if line of sight is basically VHF, is line of sight. The radio signals only go in straight lines. The other thing is they wanted to have something where there was no interference, and there is a remarkable feature of the frequency they chose, in that they're, without getting too much into the world of cosmology, because this is a PPL exercise, but there is a unique frequency in the VHF band that doesn't have any interference from space and the creation of the planets and all sorts of universal things that happens. And the frequency they chose was 108 to 118 megahertz. So it's a completely empty frequency. Nobody else is using it. It's free of cosmological interference, and it's a line of sight, and it has a completely defined range. So what happened is that the United Nations, which formed ICAO and the Chicago Convention and all the other things that happened after the Second World War, all the countries in the world all got together and they decided that this was going to become the frequency for just VOR, nothing else. No police, no fire engines, no ambulance, no nothing. This is just VOR dedicated to aviations around the world. Now, of course, the great thing about it is that as we've already said, is if you build an aerial here, the range of this signal is basically the point it hits the horizon. That is the range. And the range is 1.22 times the square root of h, where this is in nautical miles and h is in feet. So however high this is above the surface of the Earth, that's the range in nautical miles. So that means that you could actually sight an NDB here on the top of a hill, and if you knew how high the hill was and how high the top of the aerial is, you would actually know this exact range. And of course, the other great thing about it is that if you've got your aircraft over here, then you've got the range of the aircraft is also this line to the horizon here. So you've got two ranges. You've got one, the range of the NDB to the horizon, and then also you've got the range of the aircraft to the horizon. Once again, the range of the aircraft is 1.22 square root of height above sea level of the plane. So these two ranges would obviously be added together to give you the maximum range of the VOR that you can receive from an aircraft. But of course the significant thing is this range here we can determine. So that means that if this range here is, let's say it's going to be something like typically 70 nautical miles is our extreme range that we could physically transmit, we could stick these VORs in some sort of organised grid, and provided we put them sort of like about 100 nautical miles apart, one wouldn't interfere with another one. Of course, it's not to say that if you're flying high that you're not going to be able to receive maybe 3 or 4 of them. So it needs a little bit more thought than just the range of the VOR, but it does mean that with a careful bit of planning around the world, you could actually come up with frequencies for all these VORs and where you're going to stick them, so that they don't interfere with one another. And of course, when you're flying, even if you're flying, let's say 40, let's say we're 40,000 feet. well, the square root of 40,000 is 20, 1.22 times 200, let's say that's going to be 240. So even at 40,000 feet, you're looking at about 240 nautical miles. So you're probably looking at another 60, 70 here. So really, providing you're sticking them 400 miles apart on these unique frequencies, you can see that you can plan a whole mesh of these VORs. So how does the VOR actually work? Well, obviously you've got a ground station, which is basically a transmitting aerial, and what it transmits on the VHF band is it's basically transmitting a sine wave, a signal that in all directions looks a bit like this, and we call this the reference signal. And you obviously got equipment in the plane that can receive this sine wave. Now the clever bit with the VOR is, unlike the NDB, where the NDB is just transmitting, if you like, this reference signal, and we've got bits in the plane that can work out where it's coming from. We had to move a little bit on in the from the aerials and things that were contained in the aircraft, and rather than trying to work out in the aircraft, particularly when they decided to make aircraft out of aluminium and not bits of wooden things, rather than actually work out where the signal was coming from, maybe we could do something a bit cleverer on the ground, and we could work out where it is by just doing a bit more clever bits with electronics. And that's exactly what they've done with a VOR. And the way it basically works is that you can imagine you've got your aerial on the ground transmitting this reference signal out in all directions. But supposing you've got like another aerial, let's say for example, and it's acting like a radar head. So it's like rotating round, just like a radar. And what this rotating signal is doing is it's actually transmitting another signal that's you can compare against this reference signal. So what you could imagine is that we've got this like rotating radar head, if you like, and as the radar head rotates, it changes the signal in synchronization exactly with the rotation of the head. So, for example, as it rotates round, I'll draw it as a bit like a radar head rotating round. It sends this other signal out, and as it moves around, it changes the phase of the signal as it goes all the way round, and it changes the phase by, as it moves a degree, it changes it by a degree, and moves a degree, another changes a degree, until it gets all the way back to 360, and then it's back in synchronization again. So what actually happens is that you receive another signal here, and it looks like this. So in other words, you've got our black reference signal, we've got our blue signal, and if this is transmitting, say, 20 degrees, then what happens is that the angular difference between one phase and the other phase here is going to be 20 degrees. And if we've got a bit of electronics that can measure the difference between this signal and this signal, then we actually know where we are relative to this VOR. In other words, we know that we are maybe over here by just comparing these two signals. Now in reality, although I've drawn it as a rotating radar head, obviously that would never really catch on because you can't have a system on the ground with rotating things and bits and pieces, because that requires maintenance and all sorts of other things that's going to happen, some sort of calibration system. So what there is on the ground there's a series of smaller areas. So we've got this one big area in the middle which is still transmitting our reference signal, but we've actually got smaller areas arranged all the way around like this, and they form a circle. And as this reference signal goes out and produces this sine wave, then another signal is being transmitted out here that's constantly going. So it starts off going out here, then it goes here, then it goes here, and each time it goes out is actually slightly more out of phase until here it's 180, and then it goes all the way around, then it's back here again. Now the clever bit is that as we move from one of these aerials to the next aerial, we can actually sort of turn one aerial down, one aerial up, and due to the way these aerials are and their exact distance away from the centre, these radio waves will combine in such a way that it becomes a completely smooth circular path all the way around these aerials. So you can imagine that we've got a rotating head on here, but it's actually done electronically. So depending on where we are relative to this system on the ground, depending on what signal we're receiving, we can look at this phase difference again and actually know exactly which of these aerials, and not just which aerial, but also where we are relatively in between maybe two aerials as the signal's moving from one to the next to the next to the next. And this is basically how a VOR operates, in that we can have this clever bit on the ground, and then in the plane we can obviously have some electronics that will be able to tell us where we are relative to this ground-based transmitter. So this is what a typical VOR would look like. A dot showing the centre of the VOR. Surrounded by a hexagon. Next to the VOR there's a square, and in this square it will say the ident and the frequency. And on top of the VOR, there's printed on the map, there's a compass rose showing how the VOR is aligned. So I'm going to exaggerate this a tiny bit. Now I know Charlie Papa Tango is more or less on it's more or less 0 degrees, but I'll exaggerate it a little bit. So what we have is an arrow showing magnetic north, and then we'll have and then there'll be like a sort of compass rose showing so the first thing to notice is that VORs are aligned to magnetic north. They're not aligned to true north. So you'll find that on a chart the grid lines will kind of like be looking like this. And obviously the VOR will be not quite aligned with the lines of latitude and longitude. They'll vary by the local magnetic variation of the exact spot the VOR is placed. I know it's a bit unfortunate that VORs are aligned magnetic north. In retrospect, it would obviously be a lot easier for us nowadays, with everything moving on to GPS and much more emphasis placed on true north, for them to have been aligned with true north, and plus the fact they wouldn't need to be constantly readjusted or anything every couple of years. But yeah, historically, back in the good old days, magnetic north prevailed, and I mean, let's face it wasn't until sort of like 1984 did the world actually agree where true north actually really was. So back in the sort of 50s and 60s, you could actually put a special device on the ground and you could find out exactly where magnetic north was. So back in those days, magnetic north could more reliably be found than true north in a lot of ways. So they're aligned to magnetic north. So when we're using them, we've got to take that into account. So in the square, we've got the ident. In this particular case, it's Charlie Papa Tango, and the frequency in the VHF band that it's working in, 114.35. So what does that look like in the cockpit? Well, in the cockpit you'll have a VOR receiver. So I'll just show it in its simplest form. I mean, there's many permutations on a theme, but you will have typically 2 windows in the display. Some sort of button that will switch between the 2 windows, and you'll have some sort of knob, normally with another knob on the inside. Maybe this knob can be pulled in and out, or there'll be another little knob there, or something. Anyway, there'll be some sort of facility where you can twiddle this knob and you can put a frequency up here in this right-hand window, and we can put 114.35. This is the standby, and this is the active window. So typically you would rotate this outer knob until it reads 114, and then you'd rotate the inner knob till it reads 3, and you'd probably pull the inner knob and you can twiddle and get the 5 up. And then you press this button here with the arrows, and then the standby and the active swap over. So what would happen is you'd press this button, this would go 11435, and whatever was in there would go into the standby window. There'll be some sort of on-off button, and probably combined with the volume control as well. And you can probably adjust the volume of the VOR receiver. And then at the top of the stack, normally right at the very top, you'll have your intercom unit with, of course, the knob showing what unit we're transmitting from, and there's all the buttons. One that says phones, and this is the speaker row. So all the buttons along the top are the what you're listening to on your headphones, and all the buttons along the bottom is what the speaker above you is listening to. And one of these buttons will say VOR 1 or VOR or something, and you would press that button in there, and if you press this button in here that says VOR, that means that your headphones are now monitoring what's coming out of here, this box here. So we would put the frequency in 114.35 VOR, and we'd listen for this ident Charlie Papa Tango, and Charlie Papa Tango will be hopefully they work better than that. But this ident in Morse code would be continuously repeated, and you're listening for Charlie Papa Tango in Morse code. If you've got Charlie Papa Tango, then you know that you can use this VOR. If it transmits anything else, like, for example, if it transmits the ident TST, then TST is the aviation euphemism, means VOR buggered, or it's being calibrated, or something's, maybe it's been realigned back up to magnetic north for that morning or whatever. But TST basically means you can't use it. Now be careful of this, because this is a favourite exam question in the PPL exams. They'll say you're going to use a VOR, you go to ident it, and you hear the ident TST. What does that actually mean? And there's normally answers along the lines of you can't use it for IFR purposes, but if you're VFR it's fine, or there'll be another answer that says something along the lines of providing that it appears to work and you've confirmed that it is working by reference to the map or an independent source, it is safe to use. And there's all sorts of answers on that basis, but basically the answer you're looking for is if you're receiving TST, you can't use it. Now some VORs, besides just transmitting their ident, they also transmit other information. I mean, they might transmit an ATIS, for example, of the airport they're located on, and this can be very useful for you as a VFR pilot just flying around when you want to get the updated QNHs. Of course, even if you're not using the VOR system, you can still use your VOR receiver sometimes as a means of just getting the up-to-date ATIS for points on the route, and they'll quite often give you your wind, where they are. They might even give you the weather, but you can sometimes get all sorts of extra useful information from a VOR. Quite often you'll find if the VOR is down, besides just transmitting Tango Sierra Tango, they will also transmit something else, like they'll say Compton VOR unoperational, expect 1800 Zulu for when it's going to come back into effect, when it's going to come operational again, or something like this. So once you've identified your VOR and you've listened for the Morse code, you can then, of course, you can push this button to off, because you don't want to keep listening to the VOR all the time, and you can now start to use the VOR for navigation. The way the VOR works is it's transmitting these two signals, and by using this VOR receiver in the plane, we can actually find out where we are relative to this VOR. And we call these lines that's emanating out from the VOR, if you like, the radials. So this here, this is the 090 radial. This is obviously the 180 radial. This is the 080 degrees radial, and we've got a display in the plane that can help us find out what radial we're actually on at the time. So what this display looks like is typically a circular display. It has a omni-bearing selector, an OBS. And what this OBS knob does is it rotates the whole of a scale that rotates around the VOR. So let's just draw a bit in. It's 080, and then it would say like 090. And you can rotate this whole scale round and round here, and it's just free to rotate. You can rotate it in either direction. And then there's a beam bar. Now this beam bar can just move electronically left and right. So what it is just a bar that goes, when it moves from one side to the other side of the VOR. And a series of dots, 1, 2, 3, 4, 5. And the beam bar can just move left to right, and you can tell how far it's moving left to right by it just lines up with these series of dots. Now, if the OBS in this particular case is showing 080, so we've twiddled this to 080, this beam bar will go and it will move into the middle. So we twiddle this until this beam bar is sat in the middle, and that means that we're on the 080. So that means our plane in this particular instance, we will be over here on the 080 radial. Now, a little window in the VOR, and it clicks either from or to. So this is showing 080 from, meaning that we must be on the 080 radial here. So if I didn't know where I was relative to this VOR, what I could do is I could twiddle this OBS. This beam bar would be over to one side. I could twiddle it and it would go, and it would go into the middle. If I kept twiddling it, obviously it would come into the middle and out the other side. So I would twiddle it backwards and forwards until I went, and I got it nicely in the middle. So in this particular instance, if I twiddled this, and when I got it in the middle, 190 was at the top, and this said from, then I would know that we would be 190 would be on the 190 radial, which would be here, and I know that my plane would be over here. So, important points to note here is that the VOR display is showing where I am relative to the VOR. It's not actually showing what direction I'm heading in. It's just purely showing where I am relative to the VOR. And this little display inside here that's showing from and to, it's from means that we are 190 from the VOR. Now if I twiddled this around a bit more and this beam bar went out to one side, I could twiddle it, and then the beam bar would go and it would re-centralise again, and it would re-centralise on 010, and it would say 2. So in other words, for any one position, like where I am here in red, there's 2 settings of the OBS that would actually show me where I am relative to that VOR. One would be 190 from, and then it would also come in and centralise on 0102. So when it's saying from, that's actually referring to the radial you're actually on. And when it's saying to, that's basically the heading you'd have to steer to go to the VOR. So that's how you remember what is what, is that to is to the VOR and from is from the VOR. In other words, if I wanted to fly to this VOR, if I was here and I just wanted to go over the top of this VOR, I would twiddle this knob here until this went 2 and this beam bar came into the middle, and I could look up here and it would say, hang on, that's 010 takes me to the VOR. So I could then change my heading to 010 magnetic, and I could fly towards the VOR. And if I just kept this beam bar here on 010, I would eventually finish up over the top of the VOR. Now, of course, the one thing that we haven't talked about is, if you recall when we talked about NDBs and things, the problem with flying to an NDB is if you just point your plane to the NDB and the wind is blowing from this direction, and you just stick the needle of the NDB, stick the needle of the ADF straight up to point at the NDB, yes, you'll start heading towards the NDB, but very quickly you'll get blown to the right. So what will happen is you'll get blown to the right here, and you'll say, oops, hang on. Right, so you'll just change your heading again, so that the needle's pointing straight up, and off you go. And then, of course, a few minutes later, there you go. 4 or 5 minutes later, you're now here, and you keep pointing the nose up to the NDB. You keep pointing the nose up to the NDB, and if you keep doing this enough, what will happen is that you'll always be homing to the NDB. So you'll always finish up at the NDB more or less directly into wind, whereas what really we should have done in retrospect is we should have pointed the aircraft directly at the NDB, and we should have just monitored what's happening for a couple of minutes, and as soon as we were being blown to the right, we should have obviously thought, wait a minute, I've been blown here 5 degrees off to the right, so I'll now point to the NDB, but besides just pointing to it, I know that if I just point to it here, I'm going to get blown to here. But I already got blown 5 degrees here, so my needle is showing 5 degrees off to the left. So what I probably should have done is maybe, as soon as I got to here, is pointed to the NDB and maybe pointed into the wind by 5 degrees as well. In other words, what I should have done, as soon as I was here and I realised that I was being blown off course, I should have changed my heading, and I should have pointed into wind by how much I was being blown off course by, and that way what would have happened is that we would have actually have tracked to the NDB along here. So instead of homing to it, we'd have tracked to to the NDB. So we'd have been offsetting the wind. Now the great thing about VORs, unlike the ADF-NDB combination, is that offsetting the wind is actually a lot easier because it's a lot more visual. You can see what's going on. Let's have an example. Supposing we've got a wind blowing us from the left, blowing us towards the right. We've got exactly the same scenario. I'm on the 190 radial and I want to go straight to this VOR. So I've selected the beam bar in the middle, which is 010, which is what I have to do to get directly to the VOR. In other words, I've centred this beam bar 010 and I'm now going to head 010. This is what we call using it as a command instrument. In other words, the instrument is telling us where to go. We're not using it to find out where we are, we're just using it as a command instrument to determine how we fly. So 010, beam bar central, and I point the plane 010 magnetic, and off we go towards Charlie Papa Tango. I think we all know what's going to happen is that after a very short while I'm going to finish up over here. Now I'm going to exaggerate it hugely so that we can see what's going on, but I'm going to finish up here, aren't we? In other words, I'm no longer on the 190 radial. I'm now on the 185 radial. And because I'm now on the 185 radial, if I actually put .005 up here, this beam bar would go back into the middle. So clearly I'm over here, and in order to track, I've obviously got to make a left-hand turn. Now what happens in this scenario is I'm 5 degrees off to the right-hand side, and what our VOR display would actually show me in this particular scenario, it would show me that the beam bar would be here. In other words, 2 degrees, 4 degrees, 6 degrees, 5 degrees. So it's telling me that I'm 5 degrees, if I've got 010 here, I'm 5 degrees displaced out to the right. Now you don't need to remember and work out in your head, and I know it's really, really difficult in the plane to spatially work out if you're here, left or right of the VOR. So a couple of things that I would recommend. First off is we've got 2 in our flag. That means that I am flying towards the VOR. I'm going to the VOR. And I want 010, but I'm not quite there. Look, I'm just a little bit not quite on the 0110. Now the beam bar is always telling us where to fly to. So in other words, you always fly to the beam bar. In other words, what this is telling me, the beam bar is out to the left, so I've got to fly the plane and turn to my left. So what I would do is it's telling me that I need to turn left. Now how much do I need to turn left by? Well, this instrument isn't telling me how much I need to turn by, but you can see from this instrument that I've got to turn left 5 degrees at least, because look, I'm 5 degrees wrong. Now, if I turned left 5 degrees, then I wouldn't actually fly along this 010 line, would I? The best I could hope for is to parallel it. So the fact that I'm 5 degrees wrong, what we do now is I would turn left by more than 5 degrees. So if I've got to turn left by more than 5 degrees, what would be a good heading, do you reckon? Maybe 190 radial. So I want to finish up being, instead of flying 010, I want to fly maybe 000, maybe north. So this would still be 010, but I now fly my plane 000. I've turned left. So what's going to happen now? What's this going to show me? So I've turned left onto 000. In other words, I've turned left 10 degrees. Now, this is still going to show me the same thing, because what's actually happened is that although I'm here, all I've done is I've actually turned left. I haven't changed position, I'm still in exactly the same place, so even though I've turned left, this will still show the same. Now, the great thing with the VOR is we can look at the trend. So I've turned left towards that beam bar, and one of two things is going to happen. Either this beam bar is going to stay where it is, in which case indicate 5, in which case I know that I'm just paralleling that track, or it's going to start to come slowly towards the middle again, or it's going to start going further away. So if it starts going further away and maybe becomes 6, I can go, whoa, I need to turn left a little bit more, maybe another 5 degrees. And what I would do is I would turn left 5 degrees, maybe sort of 355 or something like that, and I would watch this beam bar again. And I would say, okay, is that beam bar after, say, 20 seconds, 30 seconds, is it now continuing this way, or is it starting to come back to the middle? Now the secret is to just make a trend in the aircraft. So if the beam bar is heading back towards the middle, even if it's heading back slowly, it doesn't matter. It's going in the right direction, so keep it going in the right direction. If it's already going in the right direction, don't try and correct even more and make it go even faster. In other words, just make sure that the action you put in as a pilot is going to help the situation get better, not make it worse. So maybe after about a couple of minutes, the beam bar would probably be here, say. And you've noticed that it's now coming towards the middle. After maybe a minute or two later, the beam bar would be here, almost back to the middle again. Now, if of course I didn't do anything, once that beam bar gets in the middle, it would just continue and go out the other side again, wouldn't it? In other words, what would happen is I would slowly be getting back onto this 0, 1, 0. But if I didn't do anything, I would just carry on out the other side. So as soon as the beam bar comes into the middle again, and it now aligns with the middle, I know that because I've already turned left 10 degrees, I've got to turn right maybe 5 degrees. But not go back onto 0, 1, 0, because we've tried 0, 1, 0 and we just got blown off to the right. So maybe instead of 0, 0, 0, maybe I could try 0, 0, 5. So what I would do is, as the beam bar comes back into the middle, I would then steer, say, 0, 0, 5. And I would then just keep monitoring that beam bar. So I'd now carry on flying the aeroplane, and in maybe 2 or 3 minutes' time I'd have a quick glance at that beam bar and I would see if it's still in the middle. If it's still staying in the middle, I'd think, great, I've now know that I can offset this wind by steering into the wind by 5 degrees. And this is the big advantage over the VOR, is it's very easily from a pilot to actually see what's going on, and all you've really got to do is steer towards the beam bar. So what's going to happen as we get closer and closer to Charlie Papa Tango? Well, obviously these are showing 2 degrees, so as I get closer and closer, this is going to become a lot more sensitive, isn't it? Because I only need to be a tiny bit wrong here, and I'm going to be 10 degrees off, even though I'm only like maybe a nautical mile off. I mean, I might be 10 degrees off. So as I get closer and closer to Charlie Papa Tango, this is going to maybe get a little bit more sensitive. Now, we don't want to try to overcorrect, and we'll just go straight over the top of Charlie Papa Tango, and then as we come out the other side, what will happen is that this is going to go, instead of to, this is going to click to from, because we'll be over here. We'll no longer be to, we'll be from. Now there will be a small area of confusion, like a lot of these navigational aids, is when we go exactly over the top of them, just like with the NDB, as we go over the top of it, there's a bit of and then suddenly it goes shunk, and it flies behind us. With the VOR, you quite often will get very close to the VOR, and there'll be maybe this flag here, instead of saying to, it will sort of go and it can't quite make up its mind if it's to or from, and maybe this beam bar will be getting a bit erratic, but it's only like that for typically about 10 seconds, and it will very quickly, as I come over the other side here, this will become from, and the beam bar will go back into the middle again with a bit of luck. So now I can still use the VOR as a command instrument. I haven't changed it, I haven't reset the OBS, I've still got 010 here, and I'm still flying 005. And what's happening is, it's still a command instrument and I'm flying away, and this beam bar is still moving left to right as I move left and right of the radial. And of course the great thing is it's still working in the same sense. So in other words, if I'm now tracking from the VOR, in other words I'm tracking the 010 radial, if this beam bar starts to go left a little bit, then I know that I've got to turn towards the beam bar just a tiny bit. So I've got to turn left towards this beam bar, maybe by 5 degrees, maybe by a little bit more, but I just turn left by 5 degrees, and I look at this beam bar after about another 30 seconds or a minute, and I just see if it's going left even more, if it's staying where it is, or if it's starting to come back to the middle. And exactly the same scenario would happen as if I was tracking away from the VOR and I was just writing down my time at the VOR, then I give it another minute, and if I notice the beam bar was over here, once again I would then go, oh, hang on, I'm just obviously need to turn right. In other words, I turn towards the beam bar, so I'd now turn right by 5 degrees. Pick this new heading, carry on flying the plane, keeping my heading, keeping my height. Give it another 30 seconds, maybe a minute, look down at my VOR again. Is it getting better or is it getting worse? If it's starting to get better, well, my turn right obviously worked, so I can now, if it's starting to come back, I'll wait till it gets back in the middle after turning right, and I'll turn left a little bit so that I'm, instead of turning right 5 degrees, I'll just keep it right maybe 3 degrees and just watch that beam bar, and maybe once every minute, once every couple of minutes, I'll just have a quick glance at the VOR, and I'm happy now I'm tracking away from the VOR. And that's basically how we use the VOR as what's called a command instrument. Now there are a couple of things with using VORs as command instruments which you need to be aware of. And particularly, I've picked probably one of the worst there are to illustrate this point. This particular VOR I've chosen, Charlie Papa Tango, is actually sort of just it's the Compton VOR. It's near Reading, and it's basically navigating the planes on the airway, but it's also used for VFR navigating quite substantially in the UK for just keeping you well clear of the Heathrow zone. And by tracking the Charlie Papa Tango, you miss White Waltham, you miss Booker, and it will give you a nice position to start thinking about chatting to places like Farnborough and things if you're heading north-south down the UK. Now, of course, this is an issue because it means that all over here, all up right by Birmingham and things, you've got all these planes tracking towards Charlie Papa Tango, and all these planes, when they get to Charlie Papa Tango, are all going to be tracking out here towards Sierra Alpha Mike, towards Southampton, or they'll probably turn, a lot of them will turn right, so they skirt around the side of Gatwick's airspace and head out towards Lima Yankee Delta and over towards the 2K and places like that. But you can probably see that if you just have lots of aircraft flying around in the air, the probability of two planes crashing into one another is kind of infinitesimally small, because to crash into one another, you've not only got to be at the same place at the same time, but you've also got to be at the same height at the same time, and that's never going to happen. But can you see what we've done? By making all these planes all in the Midlands, all tracking towards this one VOR, and all the planes tracking out from the VOR, and because we've got controlled airspace here, 3,500 feet, so they're all trying to fly at about 3,002, or if they're going to head this way, they're going to be they'll be flying at 2,400 feet to miss the 2,500 Heathrow area. It means we've got all these planes flying the same height, all flying to the same spot, and we've created a really dangerous situation. So sometimes VOR navigation, VFR, is not actually a particularly safe way of flying, and in fact quite often you'll find that most VFR pilots, particularly in the UK, will not fly VOR to VOR to VOR to VOR, even though it's remarkably easy. They'll use the VOR as a means of keeping track of where they are, rather than actually point-to-point navigation. In other words, unless you're really flying IFR, then really what I'm saying is that flying VOR to VOR, if you're a visual pilot, VFR in VMC, you want to think about this, particularly in the UK. So how can we actually use VORs to aid our VFR visual navigation? Well, we can actually, to some extent, use them as, even if we're not going to use them as a waypoint, because we probably don't really want to be flying over them, we can still use them as some form of reference. So, for example, let's take the typical example I've been looking at. If I just draw the M4 and Reading, the Great Splodge is over here. And Charlie Papa Tango 114.35. So we could actually, supposing we're not flying here, but supposing we are, we've got memory over here, supposing we are just wanting to have a point here on the M4, this is our waypoint here, what we could do is we could set up this point here, maybe on the VOR, and maybe this would be, I don't know, let's say this is on the 210 radial. So what we could do is we could 11435 nav We can listen for Charlie Papa Tango. And T. So we'd listen for Charlie Papa Tango. There we go. I've identified Charlie Papa Tango. I can use it, and I would set up 210 from. In other words, it's showing me the radial. And what would happen is that as I'd be flying along the M4 here, just following this as a ground feature, as I got to this point here, which I've already worked out is on the 210 radial, as I crossed the 210 radial, the beam bar would go from one side of the VOR to the other side of the VOR. So that's one way I could use it. The other way I can use it, which is actually you find a lot more, is we can actually use it as kind of like a reference. So another classic example. Let's just draw in the Heathrow zone, and let's stick White Waltham is here. This is Echo Golf Lima Mike, White Waltham. And the Charlie Papa Tango VOR is over here. Oh blimey, I can't remember what every single VOR, NDB and everything is off the top of my head, but I think my memory serves me right that White Waltham is on the 087 radial from Charlie Papa Tango. So what I could do is, once again, I could 11435, press the nav, listen out for Charlie Papa Tango. I'm not going to attempt to impersonate it again. That's it, I've got Charlie Papa Tango. I could put 087 on here, and even though I'm not flying anywhere near Charlie Papa Tango, in actual fact I'm probably flying over, I don't know, let's say Reading is kind of like here somewhere. Then I know that if I fly the 087, in other words, if I'm here and it's telling me to turn left, I can turn left and fly towards the pick up the 087 radial, or if I'm here it will tell me to pick up the I can keep flying here, turning right and sort of fly an intercept course to the 087. Then as soon as the 087, which I've got here, comes into the middle, as soon as the beam bar centralises, I know that if I then turn left, then and I've got this beam bar in the middle, I'll be heading towards White Waltham. And this is quite a useful thing, particularly for places like White Waltham, because you've got like the I can't remember exactly how it is, but you've got like a place on the River Thames here, you've got another place on the River Thames here, and another place over here on the River Thames over here somewhere, and these spots can all look very similar from the air. So what we can do is, providing we've crossed the River Thames, we can just keep flying until we've got the 087 comes in, turn onto it, and then as soon as I turn onto it, I can normally see White Waltham straight ahead of me, and I'll be able to see Reading and and suddenly all of these waypoints, these visual waypoints, all kind of make sense, because sometimes these things from the air, if you can't put them in your head relative to one another, it can be remarkably difficult at times to kind of make sense of all of this, and this is where the VOR can be very, very useful, because it just is that extra little nudge you need as a pilot in order to help your visual navigation. And you can use these VORs to great effect. So I've really only got two things to cover now with VORs. First off is that what I'd recommend is that when you're flying, if you're flying in the same area all the time and you can't remember your Morse code, is to actually just write on your plug. I mean, this is like a typical blank plug, for example, that all of us are very used to using. I mean, like, you know, I mean, I fly in Cyprus with the military, and for example, we just write down, you know, the Morse code of various VORs that we fly down. So sort of having the Morse code written on your plug. You know, in other words, don't just write down Charlie Papa Tango on your plug. Actually write down, you know, dash dot dash dot dot dash dash dot and T dash. So I'd write down the actual Morse code decode for the VOR. Now I'm going to be talking next about DME, distance measuring equipment. Now a lot of VORs come complete with a means of telling you how far you are away from them as well, which is, you can imagine that what's called a co-located DME and VOR is really, really super useful, and we can do an awful lot with VOR DME combinations, because not only do we know where we are relative to the VOR, but we know exactly how far away from the VOR we are. So that's what I'm going to be talking about next, is DME.